Munmun, you have started recording?
Yes, ma'am.
You
Yes. So, good morning, everyone. Welcome you all to the fourth day of the course. And the main topic of this day is on polarization. So, we'll be having four sessions on polarization. And the first one will be on time domain assessment of power cables, and it will be delivered by Dr. Supriyo Das. So Dr. Supriyo Das was born in 1979. He did his graduation in electrical engineering from Jalpaiguri Government Engineering College, West Bengal, and MS by research from Indian Institute of Technology, Madras in 2001. In 2004, respectively. During master's program,
Kinshuk, you were not audible for some time, so can you repeat? Repeat the bio. You were not audible.
Okay. So Supriyo Das was born in 1979. He did his graduation in electrical engineering from Jalpaiguri Government Engineering College, West Bengal, and MS from Indian Institute of Technology, Madras in 2001. During a master's 2001 and 2004, respectively. During master's program, he has worked on characterization of electrical treeing in XLP cable insulation. He received PhD in electrical engineering from Indian Institute of Technology, Kanpur, India in 2014. During PhD, he has worked on space charge phenomena in homogeneous composite polymer dielectrics. Presently, he is working as assistant professor in the Department of Electrical Engineering, National Institute of Technology, Meghalaya. His research interests are diagnosis and characterization of insulators, lightning transients, and electrostatic field computations. So, welcome, Dr. Das, and please, you can take over.
Okay, thank you, Kinshuk. Good morning, everybody. My topic on which I would like to deliver a lecture is time domain assessment of power cables. So already my introduction has been given with Kinshuk, so I want to directly go to the lecture. So just to introduce, cables are widely used in electrical system. Earlier there were paper insulated paper cables, but nowadays widely XLP cables are used. Now power network reliability depends on these cable performances. That means when the cables are under operation, they are subjected to various types of stress like thermal, electrical, environmental, mechanical, and this stress causes aging, or you can say deterioration or degradation of the insulating materials. Now, this deterioration or degradation or aging, this leads to weakening or it weakens the insulation as a whole. After some time of operation, this leads to cable failure and thereby hindering its system reliability. So, if we looking for a system, reliable system, then we need a condition-based maintenance rather than time-based maintenance. Because time-based maintenance, it means that once a cable gets damaged, then only we go for repair or maintenance. But condition-based maintenance means time to time the condition of the cable is monitored. So if there is a situation where the cable has degraded a lot, before there is any outage, we can take a preventive measure. So for condition-based maintenance, we need a regular monitoring. And efficient or reliable non-destructive assessment technique is essential. So if you are looking for non-destructive assessment, reliable non-destructive assessment, dielectric response analysis is one of the most reliable what is called assessment techniques. Basically, it takes care of the memory effect of the dielectric material. That means what is the situation of the dielectric, or what are the characteristics, what is the change in the characteristics of the dielectrics. Those things we can identify using dielectric response analysis. And it has provided with this analysis provides significant information about the dielectric material. We can carry out this in both time domain as well as frequency domain. So coming to dielectric response analysis, what is this? Whenever we apply electric field to a dielectric material, different mechanisms of polarization or conduction are activated. Now, that is under when a new sample is there, we apply a field, there will be polarization as well as some conduction. But when an aged material, we do the dielectric means when we apply a field to an aged material, in that case, the polarization or conduction is increased, means the magnitude of polarization increases, conduction increases. So polarization, as we know, that polarization is proportional to electric field. If we apply a very low field, then the intensity of polarization is less. But when we apply a higher field, intensity of polarization is higher. So polarization and electric field are related by P equal to chi. That is, chi is the susceptibility of the medium of the material, epsilon naught E. This susceptibility accounts for all kinds of polarization process within a dielectric. So if there is any degradation or deterioration of the material, in that case, this chi E, susceptibility, it reflects the material characteristics. So as I said here, means just I said that electric field, if we change the polarization is proportional to electric field. So if we increase the electric field, polarization intensity increases. If we decrease the electric field, polarization intensity decreases. But once we decrease the electric field or set the electric field to zero, in that case, depolarization or relaxation process follows. However, this process takes, there is a delay, means when we change E or we set E to zero, immediately relaxation doesn't initiate. There is some delay in it. It takes some time to initiate the relaxation process. So polarization E, that is the applied field, that is something like input to the dielectric material, and polarization is something which is an output of that input. Now this polarization by electric field, this polarization by electric field is proportional to the susceptibility of the medium. So any change with the input to output will be reflected as the susceptibility. That means it's reflected by the susceptibility. Now dielectric properties, since I said that once we change the electric field, the relaxation takes some delays, and also if there is any change in the polarization, the susceptibility also there is a time variation. So the dielectric properties becomes a dynamic event and can be quantified in both time and frequency domain. Now, if we concentrate, I will mostly talk about the dielectric domain, time domain analysis. So, if we look into this, the electric field is suddenly applied. First thing, electric field is suddenly applied. Et equal to E0 1t. 1t represents, it's a step function. Normally, it's a constant voltage. So, just to represent it in the form of time, we are representing it by unit step function, that is 1t. Now, the polarization produces the main part of charging current. That is, once we apply a field, the material gets polarized, a charging current flows through it. We can measure the charging current. Now, this polarization, there are two things in polarization. One is rapid polarization, that is, at the instant we switch on the voltage or switch on the field, there is instantaneous polarization, which is proportional to the field. Another is slow. that it takes some finite time to settle down, or it depends on the applied field and definitely on the material property also, but it settles at a finite time. But rapid polarization, it is an instantaneous one. However, in high voltage equipments, this rapid polarization cannot be recorded either in time or frequency domain. So in most of the cases, we talk about this slow polarization, that is, which settles with time. Coming to the response, means once you apply a field, then the step function, field means step function, and what is the polarization response? I have not gone through the derivation entirely, but I have just put up the equation that polarization step function that is related to a dielectric material by this integral form. It is actually a convolution theorem which has been used to get this equation. So when f of t is the dielectric response function. So once we get the polarization equation we got, now another thing is the displacement vector, that is d. Now in case of any material, isotropic dielectric material, the electric displacement increases by its inherent polarization p. So d is, that is epsilon naught e plus p. The second one. Actually, why I am showing this is, why do we do that? Means, what is the reason behind this time domain, or what is the relation between this physical thing and the mathematical thing, so that we can understand that this is from where we start the time domain analysis. So that's why first we talk about the polarization, which is is a convolution function of the dielectric response as is the electric field. Second is the displacement factor or displacement vector, that is also related to polarization. And once we consider the conductivity of the medium, then the total charging current is given by epsilon E del D del T. Like D is replaced by E, that is epsilon naught E plus P. So from there we get an equation that is Jt, that is the current density, charging current density, sigma naught E plus epsilon R del E del T plus epsilon naught del T of the function integration of the dielectric function Et. So this equation that is highlighted in or bolded, this equation forms the basis for time domain analysis or characterizing any dielectric material in time domain. So whatever the methods we will talk about in time domain, all these methods are related to this basic equation. Now if we consider the geometric capacitance in the applied voltage, because current density is something it is difficult to measure, rather we can easily measure current. So if we consider geometric capacitance and applied voltage, the current through the volume dielectric is given by in terms of Vi, that is a measurable quantity, and f of t is the dielectric response function of the insulation. So that actually gives the information about the insulation. Now coming to the methods, what are the methods in time domain assessment? The most common and most widely used method is polarization depolarization current method. There is a written voltage method, depolarization current method, or we can say it's isothermal relaxation current analysis. Voltage response method, discharge method. So all these methods comes under the time domain assessment. Now coming to this voltage current versus time characteristics, this entire characteristics shows you all the time domain analysis that can be, which we can implement. So as you see, this when we here there is one issue, that is U I have written, since the picture what I have taken is from a paper, So there you see European journal paper, so they wrote it in terms of U. U represents voltage, but we commonly represent by V. So polarization, depolarization, return voltage, depolarization current method, voltage step method, all these are represented in this time voltage current versus time characteristics. If you look at the initial stage, small t, Ch, that is a charging time, that is we are applying the voltage, UCH, there is a constant voltage we are applying. That means we will get a constant field. While we are using this constant voltage, means when we apply the constant voltage, we get the polarization current, that is IP. Okay. After charging, immediately if we don't short the material, in that case, if we leave it for some time, so small duration, that is T IDP, this time of inner discharge. In that case, some inner discharge within the material happens, and that gives a decay in the voltage, output voltage. We have applied the voltage, we have removed, after charging, we have removed the voltage and left the terminal open. At that situation, some inner discharge occurs within the material, and there is some decay voltage, that is your UD or VD. Then we short it. In that case, we will get the depolarization current or the relaxation current for time, say PDP. Now, for short duration, if we allow it to relax, and then if we try to find out what is the voltage across the material, then we can get the return or recovery voltage characteristics across the material. So this is actually a combined one. We don't do the entire thing, we segregate it. I will show you that only a part of this taken for a particular method. We just start with polarization, depolarization current measurement. Now, if you look into the schematic diagram, it's a 3-electrode geometry configuration is used for PDC measurement, and picoampere, or that's an electrometer, can be used for measurement of current. Source voltage, that is a DC source. So once we charge the material for a certain duration and then short the material to obtain the depolarization characteristics. So the voltage profile as well as the current profile, typical voltage and current characteristics of PDC is shown on the right hand side. So the depolarization current, it's a definitely a decaying one, means polarization, it's exponentially decaying, as well as it comes to a steady state, that is in the conduction level. That is what conduction current is flowing. Another one means once we short it, then depolarization current we get. And what is the voltage we applied? Something like this. We know less than T, the voltage applied is 0. Then from 0 to T1, we apply a constant voltage V0, and beyond T1, we short the sample and get or obtain the depolarization characteristics. Now, what if once we can measure this using electrometer, the currents, polarization is depolarization. Now, how to process those currents? Now, if we go back to the main equation, if we see in this IT equal to this one, with the second term, that is del V del T, since the voltage we are shorting it, the voltage across the terminals will be 0. So this factor vanishes. So what is left is the first and the third component. That is what we get here. That is I polarization equal to C0V, that is sigma naught by epsilon naught plus F of T. So when we apply the step voltage, we get a polarization current that is given by C0V epsilon naught sigma naught by epsilon naught plus F of T, where F of T is your F of T is your what is called dielectric response function. And during the step, when we disconnect the sample, we short circuit the sample, we get a depolarization current characteristics, which is just a function of C0V, means function of the dielectric response function. Sigma 0 is 0, the sigma naught is 0, there is no conduction current, only the relaxation of the material is there. So the first component again vanishes in the depolarization component, depolarization current, and what we get is only the dielectric response function. Now this Ft plus Cd, that term can be neglected when the charging time is quite large. So if we simplify it, we get f of t, which is the dielectric response function, which is approximately equal to the depolarization current or proportional to the depolarization current. So in case of PDC experiment, if we analyze the depolarization current, we are analyzing the dielectric response of the material. That is how the material is behaving. So depolarization current, in this case depolarization current represents, or it proportionally says about the dielectric response. But there are some other common parameters based on this measurement. One is the conductivity. Definitely we can find out insulation resistance, because we know if any material gets aged, that means its insulation strength is reduced or its conductivity is increased. So very common parameter we can use for assessment of the dielectric. Degree of nonlinearity. It is something which is a comparison one. We are comparing the depolarization characteristics of the characteristics obtained at a low voltage and at a higher voltage. That is IB V0. That is V0 is at a very small voltage, where just we can have a small depolarization current. But once we increase the voltage level, we may get a higher depolarization current, because in aging, means when the material gets aged, in that case there are possibilities of polarization is more because of bond breakage in the insulating material. That means the material configuration, morphological structure has been deteriorated. So definitely there will be some more possibility of polarization or more possibility of charge accumulation, these factors. So degree of nonlinearity we can get considering the depolarization current at a lower voltage and depolarization current at a higher voltage. Another one is Hammond approximation, that gives directly an information about the loss factor. So we are processing this, means considering this depolarization current at a certain time, according to the time scale, and based on that we can find out the loss factor. That is in frequency domain. From there also we can identify the aging of the material, that means the condition of the material. Another way to analyze the depolarization current is the extended Debye model. Actually, these are mathematical analysis. We take the depolarization current and then we try to fit this depolarization current in a RC model, where we will get time constants, this RC parallel branch, as I have shown here, that R1 C1, R2 C2 to Rn Cn. Each of these branches represents a different characteristics of this polarization or depolarization. For example, in case of water-treated XLP, there are three branches are considered to explain the relaxation process. The first branch normally represents the dipolar polarization. Second branch represents the what's called interfacial polarization. Third one, the water-treated polarization. So they have a different time constants, and based on the time constants, we can identify what are the types of depolarizations are occurring. So the entire depolarization current is segregated into small relaxation components based on the time constant. And from there we can identify the condition of the material. So these parameters we can obtain, this this time constant parameters of Debye model, these we can obtain from the depolarization characteristics using some methods. Sometimes we fix the time constants or we use some optimization technique. For example, I have shown this extended Debye model. If you look into the black one, that is the entire depolarization characteristics, and this entire depolarization characteristics, there is a measured one, is segregated into 9 branch, that is R1, C1, R2, C2 in this 9 branch. So they have a different characteristics and they have a different time constant. So from there we can again analyze. If we analyze this, we can identify the aging criteria. And the second one I have shown about the loss factor in terms of frequency. It is not a frequency domain analysis, rather it's a time domain we are converting it into frequency. This is the difference. So here also, if you see, I have shown examples of an unaged polyethylene and an aged polyethylene. In case of aged polyethylene, if you see the characteristics at the frequency range between 10 to the power minus 3 to 10 to the power minus 1, the loss factor is higher. So there is a difference in the characteristics of an unaged and aged polyethylene. So from here also we can identify or we can assess the condition of insulation. Next, coming to the return voltage measurement. The return voltage measurement, the schematic diagram of the experimental setup is shown. So initially we will charge the sample, close the switch S1 and charge the sample for a time duration, let us say T0 to T1. Then S1 is open and S2 is closed. That means we are disconnecting the supply and shorting the cable insulation for a small time, T1 to T2. And then we open the switch S2. This is during T2. So whatever the residual polarization is present in the sound dielectric that is built up across the dielectric, we get it in the form of a voltage characteristics. So if we look into the voltage characteristics of the return voltage measurement, we initially charge the sample for a certain duration, then we short circuit the sample for a very short duration and measure the recovery voltage across the insulation. We get a characteristics, it rises and then decays. Mathematically, if we want to express, we get this equation, that is the V del T, that is the rate of rise of voltage, which is proportionally related to the dielectric response function f of t. So, in case of polarization depolarization current measurement, the dielectric response function or the dielectric response is reflected in the form of depolarization current, whereas in case of return voltage measurement, the dielectric response is reflected in the form of rate of change of voltage. Okay. So here we measure either the maximum recovery voltage, return voltage, or we measure the slope of the return voltage, time to maximum return voltage. If we measure these parameters, they reflect the aging conditions. So this is a method to investigate slow relaxation process, basically. This method has been used widely in impregnated cellulose HVDC cable insulation, oil paper insulation. It has been widely, there is a lot of literature on this. where it identifies the moisture content. In oil paper insulating paper can what's called absorb moisture. So then how much moisture is contained in the paper, that has been widely studied using this return voltage measurement. Thermal aging of paper insulation, water trees in XLP cables. So till this return voltage measurement is under research. A lot of work is being done because particularly in oil paper insulation to quantify the moisture, this RVM method is widely used. But for other purpose, still people are working on it. Now, what are the parameters that can assess the condition of insulation? So, already we said the initial slope of the return voltage, time to reach the maximum return voltage, and the maximum value or peak value of the return voltage. These three are the basic parameters through which we can assess the insulation. Now, there are different methodologies, techniques to use this return voltage measurement. One is single point test. Single point test means we do one test, only single test, and then we find the recovery voltage, slope, peak time or peak voltage, but it does not contain much information. So 4-point tests gives a comparison about, means it is done under 4 different voltage. This voltage means charging voltage, we are applying that voltage. So let us say 0.5 V, V, 1.5 or 2 V, at 4 different voltage, we charge the sample and then try to calculate the recovery characteristics. There is its slope, its peak value, recovery voltage peak value, time to peak value, and then do a comparison. Because sometimes at low voltage we get less amount, because if we do it in 1 voltage, we may not get any information. If we do it in 2 voltage or 3 voltage, we have one lower voltage, we get some result, very low voltage, that may not affect the insulation either. So that we can take as a reference, and then with respect to that, we can apply a higher voltage for charging it, and then we can make a comparison and then identify what is the situation. Polarization spectra. This is somewhat accepted method to for return voltage measurement. What is done is a series of return voltage measurement is performed with increasing charging time and keeping charging time to discharging time constant. That is, TC is the charging time, TD is the discharging time. This ratio remains constant. If we assume 2, let us say TC by TD is 2. That means if we charge this material for 2 hours, we apply the voltage for 2 hours, we will discharge it for 1 hour. So that ratio is maintained, and then for a sequence of charging time, we measure this return voltage characteristics. So mostly we plot the slope, that is a rate of change of return voltage, there is the initial slope with charging time, or we measure the return voltage peak with charging time. So once we get that, then we measure, compare it, and then we try to identify. The charging and discharging process is repeated using a sequence of increasing charging times, range from, that is what I said, from seconds to thousands of seconds. We change the charging time from small, even in 1 second, 2 seconds, to even some 1000 seconds, 1800 seconds, or 3000 seconds, to that range. Another is division spectra. It is a multiple polarization spectra, where already said that TC by TD we maintain that ratio fixed. Now here we are changing the ratio and then again doing the same polarization spectrum. It has been seen that this works for few what is called assessment techniques, means for analyzing these cables, this also works with a, or gives a better information. For example, I have shown here two plots. The first one, there is an XLP, aged XLP, which is aged for 3 hours and 9 hours at a high temperature, around some 120, 130 degrees centigrade. And then the return voltage measurement is taken. It is seen that the 9 hours, if you see, the 9 hours represents the dark bar and 3 hours represents the light colored bar or gray bar. We have scanned, this is scanned for from 0.02 to higher seconds, and every time it is seen that the 9 hours bar dVdt, that is the initial slope of the recovery voltage, is higher compared to the 3 hours AG. So this indicates, means from the graph itself we can say that the 9 hours which was aged, or cable was aged for 9 hours, that cable has undergone a thermal aging compared to 3 hours. So just from the rate of change of slope of the recovery voltage. In the second one, we have taken the maximum return voltage, or B peak, that I have shown. So in this case, again with a different charging time, it has been plotted, and the first peak, when it is plotted with the charging time, the first peak, that is this region, that is called the dominant time, or dominant time constant. If there is any change in this dominant time constant, then there is some form of aging. For the paper 2, particularly for this characteristics, it is mentioned that since there is no change in this dominant time, that is the time to first peak, since there is no change, they have concluded that there is no moisture content within that cable. So it's just an example to show how this can be used for assessment. In the earlier case, we have shown that dVdt, if it is higher, that represents aging, means aging is more in that case. And in the maximum return voltage of two samples, so aged samples, for aged at different 3 hours and 9 hours, again same thing, there is no change in the dominant time constant, which basically means the time to first peak. If there is no change, they have concluded that there is no moisture content in the cable. So these are the way we can identify the aging parameters or aging factors of the cable, or we can monitor the cable. There are some other assessment parameters also through which we can assess the power cables. There is increase in stiffness of the decay, that also indicates some progress in thermal aging. Dominant time constant, as I said, is a significant characteristic of the polarization spectrum. It is dependent on the properties of the insulating material and directly reflects the moisture content of the oil paper insulation. The displacement of the curve peak towards small time constant indicates degradation of the insulation system. Depending on moisture content, maximum recovery voltage attained may vary with shorter or longer charging time. The other assessment techniques means just analyzing the same results in a different way, we can identify the aging parameters. Current to depolarization current method, or isothermal relaxation current analysis. So isothermal current analysis is basically we are using the same depolarization current or relaxation current, the measured values, and then mathematically processing it to obtain this isothermal relaxation analysis. Nowadays it is done using some software also. So relaxation current, we can represent it, or we can say it is has a one constant part, and sometimes there is no constant part even. It's only some what is called exponential components make up, different exponential components make up the relaxation current. The same thing is applicable for the extended Debye model also. That one depolarization current is made up of different current components, different relaxation current components, which has a different relaxation times constant. Okay, the same thing is here also. Only the thing is the mathematical analysis is different for the extended Debye model and as well as IRC analysis. Different current components are dependent on specific mechanism of charge trapping, aging. So based on those components, we can again analyze. It's already said whether charge is trapped or not, whether aging is done or not. These things we can identify. So basically, the concept is mathematical evaluation of the transient part of current is based on relaxation model of thermal release of charge carriers from traps. So it is a relaxation model when means charge which gets trapped in the insulation, if they are released under thermal stress. Based on that, this relaxation model is used actually. So what we do here to analyze the discrete traps, that is IT, that is the current multiplied by the time versus log of T. This is the plot which we which is plotted actually, IT versus log 10 of T to the base 10. So this analysis of discrete trap levels in the form of this plot, that is IT versus log 10T, enables the determination of the aging process of the insulation. It basically indicates energy distribution of the occupied traps in the upper region of energy gap, that means in the shallow region, describing the aging behavior of insulation. It is observed by some researchers that the escape frequency, if it is around 10 to the power 11 Hz, then IRC evaluation takes trap energies from 0.63 electron volt up to 0.84 electron volt. That corresponds to IRC measuring window of 5 seconds to 800 seconds. Means if IRC measuring window, we measure it within this range, and if we assume the escape frequency is 10 to the power 11 Hz, in that case, it is seen that the trap level varies from 0.63 electron volt to 0.84 electron volt. So this is an example. Again, I have shown few graphs. So in the first one, that IRC curves of aged cables at 120 degrees centigrade aging temperature. So it is aged for 20 days, 30 days, 40 days, 50 days. So isothermal relaxation current versus time is plotted. That is depolarization time is plotted. But if you look into the picture, it is very difficult to separate out between the aging. That means what I want to mean is between 20 days aged, 30 days aged, or between 40 days aged and 50 days aged. It's very difficult to separate out. So to understand these characters, definitely there is some form of aging, but we are not able to identify that aging. Like 20 days aged and 30 days aged. So in order to understand that whether there is anything or not, in some form of aging is there or not, this isothermal current, that is IT, the current into time versus log of T is plotted. And if you plot it, the left hand side below, left hand side plot, if you see, we get a separate 4 characteristics. So one is black, red, blue, and pink. So we get 3 separate characteristics. And when there is the first peak, of a particular characteristics that is taken as the time constant, tau 1. Now we can segregate. Now we can say 20 days aged. See, that was the least aged material. 50 days aged. That is the most aged material. So there is a significant difference between the different aged materials. We can identify that. And from this IRC plot, we can find out the trap levels even. That means because when there is aging, there is breakage of bond. So whenever there is a breakage of bond, that means, for example, let me say, polymers are mainly made of CH bonds. Now, if there is any form of aging, then the CH bonds will break. C may have means possibility that it can capture some other ions or positive ions. H has a possibility it can capture an electron and get neutralized. So these materials, if it captures some positive, let us say C, if it captures some positive ion after bond breakage, if it captures any positive ion and gets neutralized, that means that particular positive ion is trapped. So because of aging, such breakage of bonds is more, the deterioration is more. So in that case, formation of traps is also increases. So IRC analysis, from IRC analysis, we can identify those trap levels which are the trap levels of aged materials. If the trap level is very high, that means, let us say this, if you can see here, the black one, that is 20 days aged. The aging is less compared to the blue one, that is 40 days aged. So the trap level in case of the 20 days aged, that is black color, is around in the range of 0.75. So if you look here in the first row, that is black one is at 0.75, whereas in the red it increases some more. Again, it increases more for the blue. So we can identify the trap levels that is associated with the aging. Voltage response method, that is the fourth one. In this case, we actually measure two slopes. One is the slope which is related to the recovery voltage, return voltage, and another is slope due to internal decay of the voltage. So internal decay of the voltage means that SD, once the material is charged and then the supply is switched off and left it for a short time so that the internal decay occurs. So this internal decay or internal decay voltage is decay in the voltage. So the slope associated with that decay voltage is SD, and that is proportional to insulation conductivity. And then it is shorted for a very short time, and then we measure the return voltage. The initial slope of the return voltage is your SR, which is proportional to the polarization intensity. So based on the measurement of decay and return voltage, this voltage response method is used. It is also, you can say, is derived from return voltage method. So SD, the slope of the decay voltage, is plotted as a function of slope of the return voltage in log scale. And based on SD and SR, that is the two slopes, it is possible to differentiate between the degree of thermal degradation and moisture content. If you look into this picture, the first one, it shows there are four cables, cable 1, cable 2, cable 3, cable 4. On the y-axis, the stiffness of decay voltage, and x-axis, stiffness of return voltage. If you see cable 1, cable 2, Cable 1 is represented by triangle. Cable 2 is shifted towards the right. There is a square, then rhombus. It is a little bit higher up, and the circle one is quite high. What it means? The position of the points show the condition of the insulation. Displacement to the right shows increase in thermal aging. That means the cable 2, cable 3 is shifted compared to cable 1. It is a triangle marker. So it represents that cable 2, cable 3 or cable 4, as it has shifted towards the right, it has higher thermal aging, higher degree of thermal aging or increased thermal aging. And if there is a displacement, if the marker shifts upward, vertically upward, in that case it indicates increase in moisture content. So if we consider cable 2, 3, 4, cable 4 has the highest moisture content because it has shifted higher up compared to 3 and 2. And also, if you look means in the horizontal direction, in that case, again cable 4 is more aged, thermally aged compared to cable 1, 2 or 3. So in this way, we can identify the aging of cables. You can assess the cables. The same another graph is it is with PILC, paper insulated lead coated graph. Here also it is shown that there are two types of materials, and based on the ratio of SD by SR, we can identify whether there is any thermal aging, which one has a more, which is more thermally aged, or which is more moisture content. Next is the discharge current method. In this case, we are using this internal discharge decay as well as the depolarization characteristics. The cable is disconnected from the direct voltage source and from every discharge device. That means we are removing the voltage and leaving it as it is. So depending on the condition of the cable, dielectric inner discharge occurs. So maximum the depolarization current is measured as a function of charging voltage. There is one way to assess the insulation, and another one is initial slope of the decay voltage is measured as a function of charging voltage. So either SD or ID max, that means we can measure it, that is depolarization current versus charging voltage or slope versus charging voltage. But in either one may not reveal the single standalone may not reveal sufficient information. So some empirical formula is derived, which is called electrostatic value. So based on the value, it is calculated based on the polarization current, depolarization current, charging voltage, time to charging voltage, time to discharging. So considering all these factors, an empirical formula was proposed, which is called characteristic value. So based on those characteristic value, we can again assess the cable. What is the status of the cable? There is something given like this. If there is CV, that characteristic value, if it is more than 10, then there is no remarkable signs of aging. But if it is less than 1, that means it is heavily aged and it may lead to breakdown very shortly. Okay. So these are the 5 methods which are used in time domain for assessment of cables. I would like to conclude here with the following points. The time domain method offers better opportunities for assessment of cables. PDC measurement at laboratory level is carried out on many high voltage equipments. It's not limited to cables. even on high voltage rotating machines, transformers, J-Tenor arresters. Regional voltage method is less explored for assessment of aging in cables, mostly used for transformer insulation. Nowadays, artificial intelligence techniques are being used in IRC analysis. Voltage response method and discharge current method, these are very less explored. More work can be done on this area. And always combination of two measurement techniques provides better insulation, better assessment of insulation, because one may not be. So if we have two, we have more significant confirmation about the assessment. So some references which I followed for this presentation, and that's all from my end. Any questions?
Thank you, sir, for a very detailed talk on time domain analysis. So we have the first question, from Shomadip Chaudhary. What is the physical significance of the dielectric function Ft?
Physical significance of the dielectric function. See, I have one question. Is physical significance means what you want to mean? Means.
Shomadip, you can ask the question directly.
Hello, is it audible?
Yeah.
Sir?
Yes, it is audible.
Sir, I wanted to know that what does it represent? Means in reality, what does it represent? That f of t.
See, f of t. Okay. Let us say we have aged one XLP cable, right, at higher temperature.
Okay, sir.
The other thing is, definitely there will be some degradation of the material, because it's the material itself will degrade. What I want to mean, we apply a temperature at higher temperature, which was supposed not to be, so we are not about to apply 120-degree transition temperature. Okay, let me explain in this way. XLP cable, let us take, we are applying a higher temperature to it, that will undergo some form of degradation, definitely. Now, another cable we will apply, say 80 degrees centigrade temperature. The degree of aging will be different for both the case. That means one with applied with 80 degree and another one with what is called 120 degree. Now, how will you identify that? We can identify it means from electrical point of view. We have some physiochemical analysis from there you can identify. But from electrical point of view, how do you identify that? So to identify that, this what's called dielectric response function, that actually gives you that which one is more aged or less aged. If we find the depolarization characteristics of the material which is aged at 80 degree and the one which is aged at 120 degree, we will get a difference. Because in case of 120 degree, the aging is more, polarization will be more, whereas compared to this 80 degree centigrade. So when we compare these two, we get to understand which one is more aged. So that is reflected by this dielectric response function.
Okay, but thank you.
Next, we have question from Chirag. So 120 C is transition temperature of cable. If above 120 degrees centigrade, what should be the effect of VDV?
If above what should be the effect of breakdown voltage? Cable means, I guess you want to say about XLP cable. Its melting temperature is around 130 degrees centigrade. Now, 120 degree, above 120 degree, means if you go to 130 is already a melting temperature of XLP, if I talk about. then definitely it will affect the breakdown voltage. Because when we are heating it, we are feeding thermal energy into the material. When we are feeding thermal energy into the material, definitely its molecular structure will get loose.
Okay.
So if the molecular structure is becoming loose, then its breakdown strength will automatically be reduced in that temperature.
So any empirical formula or any coefficient is there direct relation with BDV and temperature in case of cable?
In case of cable, as of now, I don't remember. Maybe I have to look into it.
Okay, sir. Thank you.
Next question is from Niharika Barua. Is the switching done by a mechanical toggle switch?
Yes, you can do the mechanical toggle switch itself.
Okay, next.
Yes.
Nileshwar asks, in case of HVDC, it is known that XLP cable is not suitable where polarity reversal is taking place. You could provide some explanation for reason degradation mechanism due to polarity reversal.
In case of HVDC, it is known that XLP cable is not suitable when polarity reversal is taking place. Polarity reversal means under what context can you, if you can say something on this? Sure.
Hello, am I audible?
Yes, you are audible.
Okay. So actually, sir, in case of LCC HVDC, when we have to reverse the power flow direction, the voltage has to be reversed. So because we cannot change the direction of current in case of LCC, so we have to change the voltage polarity. So positive 500 becomes negative 500.
Yes.
So, and that is it means the manufacturer say that XLP cable is not suitable for this LCC project. But in case of VSC projects, yes, we can maintain the same polarity always because we can change the direction of current. So there it is suitable. But in case of LCC, the cable XLP cable is not suitable because of this polarity changing with respect to the ground. So
One thing there is, I'm not much sure about it, but possibly uh, this polarity reversal. I think, what do you mean by LCC? That can you explain me?
LCC is the HVDC which is based on the thyristor. So far in India we have approximately 10 projects which are always based on thyristor. So thyristor because it is line commutated converter actually. LCC is
Okay,
based on
okay,
the
okay, okay,
so
okay. Exactly, I cannot give you right now the answer, but my
phone કર્યો હતો પણ તમારે no reply.
If I may interrupt Dr. Das,
Chirag.
if I may interrupt Dr. Das, maybe it has got something to do with the space charge trapping.
yes, ma'am, that is what I was thinking about. Possibly it is related to space charge trapping, but since because he is saying for some other purpose, it is not an issue. That's why I have a question on that.
I'm also not sure about, yes. What are the different applications he's talking about?
Yes, yes.
But we don't know the exact situations there.
Exactly.
Yeah.
But possibly it may be, in this case, it may be due to space charge, we may not be able to reverse the polarity. Maybe.
Okay, so next question is, what do you mean by residual polarization?
Residual polarization means, see, when we polarize a material, there are many different polarization mechanisms happen. Let me in short say, there may be atomic polarization, which when we relax, that means when we switch off the supply, it relaxes very fast. Then there is dipolar polarization. It takes some time to relax. Then there's an interfacial polarization maybe. It takes more time to relax. So when we switch off the voltage, immediately this atomic or ionic polarization or dipolar polarization relaxes completely. But there are other polarizations, space charge polarization, hopping, tunneling, interfacial polarization. This remains. It takes long time to relax. So residual polarization, when you want to mean, it represents that part of the polarization that is beyond this dipolar, you can say.
And Niharika has one more question. Is there any shield box provided around the sample to handle the sensitivity of the instrument?
Shield box provided means, see, when we are measuring using electrometer, particularly we use for low current measurement, we use only electrometer. In that case, the electrometer, the measuring cord itself is a shielded one. Okay, so possibility of noise means it is less, comparatively less.
So is there any further question? I think no. So thank you, sir, for your talk.
Okay, thank you.
Okay, we will start our next session from 12 o'clock about frequency domain.
Just a minute. Thank you, Dr. Dash, for your very interesting and illustrative talk. And you have set the background very nicely for our interaction session with Professor Raju this evening, about which you would have all have received information. The next talk is also going to tell us a little more about polarization from another aspect. Thank you, Dr. Das, very much.
Thank you, ma'am, for giving this opportunity.
Thank you, Dr. Das. I'm Alok. So I'd like to thank you for a wonderful talk. Yeah.
Oh, thank you, Dr. Verma. Thank you very much.
Dr. Das, we have one more question.
Yes. Why recovery voltage is produced, return voltage is produced in a previously DC stressed transformer insulation? Voltage is produced in a previously DC stressed transformer insulation after incomplete depolarization. Yes, it is possible. See, it is an incomplete depolarization. We have not completely relaxed it, right? So since we have not relaxed it, or we have not allowed it to relax completely, definitely some form of polarization is present. So whenever we try to measure the voltage, that is a recovery voltage, we will get it. That means we can obtain the recovery voltage, we can measure that.
Okay. Thank you, sir.
Thank you, everyone. Thank you.
So the next talk will begin at 12, and I will just make the announcement again that we have sent you a mail yesterday. So if you have any more questions about polarization and any more doubts about it regarding your work or anything, you can fill in the Google form and with your question. So it will be answered in the last session of the day from 5. Thank you.